Hey guys, how are you all doing? As for myself, it seems like Kotlin Heroes and Sleeping Badly are just like linked together for me, so it's just how it's gonna be. But yeah, we're back here. I'm using Java once again. Basically, the way my setup works is, I just have this stuff that basically it's like my normal compilation command, except it's for Java. And so what that does is then I can just run this normally. And then I'm writing in Java, and then I'm using IntelliJ to convert it to Kotlin. You'll see how I do that later. It's really simple. But I'm not actually using Kotlin, so it's more like Java Heroes or whatever. That's the plan. I think everything works. We should be good. Let's go. Trying to get top 50 again. So, Kate Day. From the LF day to the RF day. Vika's friends. Huh? Wait, how's this work? Oh, no more than one friend's house. Okay, so we just take the maximum. Sure. Why's my typing so bad? I swear it was better 2 hours ago when I was doing the practice contest. Okay, so essentially, if the interval contains the kth day, so if L is less than or equal to k, then ants is equal to max ants r minus k. Is it plus 1? Do we need to add 1 here? R minus k, I guess, yeah, plus 1. We have multi-tests, we do. Math.max. 401. Yep, okay. R minus k plus 1. Seems good. Yeah, we're using the most one friend. Okay. So I think this should work. So basically I just paste it in here, and IntelliJ is just like, do you want to make Kotlin? And then I do, and then it's perfect. Yeah. So unfortunately, it probably means the video is gonna lag a bit more, just because it's like an IDE and it's probably gonna eat up some computational power or whatever. So it could be a bad thing, but I kind of don't have a choice. So I'm sorry if that happens. Guess I'll open everything. Okay. Nearest point function. For a given array of integer points and a point y, can find the nearest point from x to the point y. So determine if any adjacent difference is even. Okay. That's it, right? Is that really all it is? I mean, yeah, I guess so. No, wait. Yeah. Yeah. If any adjacent difference is even, you pick the point between them and then it works. If not, okay. Sure. 10 Is it sorted? Yeah, it's sorted. AI mod 2 is equal to 0. So we're looking for any even adjacent difference, then we put the stuff in the middle, and then I think that should work. So then if we have any even adjacent difference, then false, true. Yes, no, 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 yes, yes, no. Okay, I don't understand what they're going for here. I guess it's fine. I'll take it. We're doing fine, right? I hope the audio is working still. Seems like it's okay. Also, yeah, there's a bit of stuff I have to do to make it like the Kotlin conversion actually work, which is slightly annoying, but I guess it's fine. Can we pass? Cool. Alright, so goal is just top 50. So right now I'm actually okay. And delicious sweets on a circle table. Eat all the sweets that are on the table. However, eating them in a random order is too boring. So if there are no sweets that she likes. Oh, okay, okay. So at the very beginning of the game, if there's at least one sweet, she eats the sweet number 1. Counts K sweets clockwise. But it's 5,000. Okay. But it's 5,000. Okay, sure. So basically we just brute force. Because, yeah. Did I call it end stir? Yeah, okay. Alright, so so boolean this equal new boolean n. Get, wait, char at, right. 1 characters are primitives, so I can do that. Plus count. Int jump is equal to k while jump is greater than 0, pause is equal to if not visited pause, then this counts as one that's still in the array, so we subtract it from the amount that we're jumping through. So if, that's for the number of jumps, right? Yeah. So if, what are we asking for? S dot. So if this is a 1, then we decrease the count of the 1s. This is simply the number of 1s, so that if it ever reaches 0, we're done. Yeah, seems fine. Multi-tests. Oh, that's a problem. 7 somehow. Oh, that's why. This pause equal to 1. True. Okay, now it prints the length of the string. What? Okay, so 3, 2. I need to print the answer for reference. Okay, so 0, 1. Okay, so we eat sweet number 4. Oh, wait, this matters. Okay, maybe this changes everything? Slight issue. And then it doesn't stop running. What? What is going on? What am I doing wrong here? So we count the ones. That's the first step. Now, while the number of ones we still have is greater than 0. So we increment the answer. If this current character is 1, decrement the count, set this visited to true. Now jump k things forward. If we have not visited this position, then it counts as something. What is this stopping on? Oh, wait. If count is equal to 0, break. I see. Yeah, okay. Cool, that seems fine. Yeah. I think that was it. I think that's the only, I hope that's the only issue. I mean, it's up to 5,000, so looping should be fine. Now we don't have any infinite loops because this will only run if count is greater than 0. Yeah, okay. Kind of trust it. Could be a bad idea to trust it, but I don't know. String searching. Cool, strings. You're given array S. Test 7. 1357. Wow. I guess that's n squared for you. Cool. Wow, tourist is tied. What is he? I guess he's falling behind, huh? How goes second thread? Still doing it. Q queries. Each query is a string t. Count the number of indices I such that. What? Okay. Q queries. Each query contains a string t. If it is allowed to insert one letter in an arbitrary position. Cool. So I guess we can generate the strings that work. Well, wait, how do we do this? So M is almost 10, which is kind of expected. I'm gonna make a try, but that's dumb, so let's not do that. Okay, instead we just consider removing a character from here, and then, yeah, okay. So instead of like thinking about the other string, about the like given strings, we think about like removing a character from the query strings, and then that gives us some unique ones, and that's fine, I think. So essentially, M is not helpful. Tree map string integer count. I have to remember documentation. Okay. If count.contains key s count.put s count.get s plus 1, else count.put s 1. There's a slightly better way to do that, but I don't care, it's already written. Now, for string pause equal new string n plus 1. So generate the strings that can be generated. Pause j is equal to r dot substring. So it's from 0 to j plus r dot substring j plus 1 m plus 1. No, just to m. Alright, so we also have to like be careful about that. So we can like, if j is greater than 0, we can do that. If j is less than m, right is equal to. Right. Yeah. J plus 1 and plus 1. Cool. So then this is just left plus right. So if this is the same as some other string, if pause j if not, we only count unique strings because we don't want to count a string twice. Because we're not saying of all the ways to insert a letter, we're just saying if we can insert a letter, how many matches do we have? Okay, so if count dot contains key, pause j, Nance plus equals count.get pause j. Ideally this is fine. It is not fine. Am I trying to read in a string as a number? So I can do this here. Maybe that's faster and not declare a bunch of arrays. And I'm kind of concerned about time here, because it is 10 to the 6th operations. I mean, wait, 26 to the 10. I guess we could do hashing. Let me see how the status is for D. 1169. I guess it's fine. No, actually, it's probably better to hash. Yeah. So it's lowercase letters. 27 to the 10 should also be fine. So what is this? Parse int main.solve 33. Old 33, now we have to recompile. Why? Hey. Stop care at I. Okay, what? 42. Oh, I'm reading test cases, right? Two 201. How? Pause k is equal to pause j. Match equals true. Break. Oh, right. Because we need dot equals, woohoo. Okay, so long, let me do long. Okay, so now we just like do the hashing or whatever. Pause check. H. Hashes should be unique because it's a small space. 1321 now. Okay, this should be fast. I hope. Yeah. Looks like hash map also exists, but whatever. Anything is fine. Actually, a true map would be terrible. Hash map is more fun. Okay. Still concerned about the time limit. I guess we're fine. Okay. 1278. That is kind of close, but it's not that big a deal. Okay, let's get to the harder ones, please. Something not code. Okay. Polycarp is... Audio is still working, right? If I touch this, it's fine. Hope so. Polycarp is coaching a team. Complete team should be n+1 members. There are n members. They have a skill. You have to choose a final member. Difficulty of a game for certain players. The difference between his paired opponent's skill and his own skill. Maximum difficulty of all its players. Oh, it's queries, I see. Okay. Alright, so how is this going to work? Essentially, we're sorting the two arrays, and we compare the differences. Are we supposed to do signature stuff? No, I guess we don't have to. It's basically just like prefix and suffix match max, right? Yeah, it is just prefix and suffix match max. Okay. Essentially, the way I'm going to do this is we have like the B people here, and then essentially we're going to put this person down here, and the rest of them are going to match up like this and then like this. So A is going to be sorted. B is going to be sorted as well, and then this is going to be in the position where it's like it works for the sortedness. So essentially there are three components. We need the maximum of this part, and of this part itself. So this part's easy, we just check it directly. For this, it's essentially the suffix max of these elements, considering that the red elements are over here, and then this is similarly the prefix max. So we can build the suffix max over here, assuming that like the green one is to the right of that, and then like everything should work. So new int n r sort A, r sort B. This is sort of like second thread Shannon ruffle, I think that's no, what is it called? I don't remember what it's called, but it's like you just shuffle the array and then you do it like that. -5. Huh. Interesting. Okay. So you can't have negative numbers. Alright, so int pmax. This can be fine, right? Send the 9th, yeah. So negative. This should be, let's see. It's barely fine. Actually, it can't be worse than -10 to the 9th, but whatever. So for int I equals 0, I is less than n, I plus plus, r is equal to max r bi minus ai. P max I is equal to r. We don't care about the last one because we're never going to access that anyway. So r is equal to that. For int I is equal to n, I is. So this is the suffix one, bi minus ai minus 1, because now we're like matching this to this, and so all these indices have to be shifted over by 1. So s max I is equal to r. So now we read in the queries. Int q equals in.int. For int I equals 0, I think qi plus plus. Well, like fast IO is fine, right? Like I have the scanner stuff. Int x. Okay, so right, so essentially we do binary search now. Int L is equal to 0, R is equal to N, M is equal to L. So we're finding the element that it's less than or equal to. We're finding the last element such that this is less than or equal to it. Okay, so we know it's sorted. We want to find the last position where this is still less than or equal to. So if a m is less than or equal to x, is that what we want to do? I'm kind of confused now. Because being an n should also be an option. Wait, okay. We want to sort array. I'm literally forgetting how to binary search. And we start in the middle. God, I'm so tired. We have a sort array. We want to find the first position where this is going to be less than or equal to this stuff and maybe greater than this stuff. So we look here. If it's less than or equal to, then we actually want to go this way. No. Yes. It's going to be harder for it to be less than or equal to a value here. I'm genuinely forgetting how numbers work. R equals m. Right, so if it's less than or equal to nothing, then it's fine. We want it to be at the end. If it's less than or equal to everything, we want it to be at the beginning. Sure. So int ants is equal to negative this. If L is greater than 0, ants is equal to max ants p max L minus 1. If L is less than n, ants is equal to max ants S max L plus 1. Ants is equal to max ants, actually, BL minus AL. Right? Yeah. That was less than n. Yeah. Math.max. I don't like Java. I don't know if I've mentioned that. I know how to use it because it's been drilled so hard in school, but I don't like it. Just gonna... Doesn't even allow shadowing? Oh my god. Okay, this should be fine now. Assume it breaks. The hell is it printing? What is it printing? What are you doing? I'm not even okay. Yeah, that makes sense. I'm not even reading the arrays. What am I doing? Then equals, because we have one more element here, and then b. Cool. Where? 72. Oh wait, b minus x. Yeah. Eight, 4, 4, 4, 4. Why? What happens here? This is weird. Okay, so it's just like messed up. Wait. It's b minus a. We want to sort, right? Is there any case where we would not want to sort? We want the biggest AI to be with the biggest BJ. X. L. I'm gonna make this an ln for now, just to see everything. Seven, 6, 4, 8. Oh, it's always 0. Okay, why? Why is it always 0? Now we debug binary search. Cool, love that. So 1, 7, 6, 4, 8. So that's intended. But for 7, oh wait, that's why, because I'm reversing the condition. Which still actually doesn't make sense to me, but why would it get 0 for everything? Oh wait, it's because it's sorted, so it's messed up. Okay, I'm not gonna question it. I think it's fine. I think it's perfect. It all works now. Zero, -5. Right. Okay, so we're doing prefix max and suffix maxes. bi minus a, I minus 1, because we have to shift the array by 1. Then we do binary search. If x is less than or equal to that, then wait, what does it mean? No, we're looking for the leftmost position that it works for. So if x is less than or equal to am, then set r to that, because we want to go to the left. Otherwise, we have to go farther out to the right to larger numbers, so set L to greater than. Yep. So P max L minus 1. L is less than n. That means L can be equal to m minus 1, so L plus 1 equals n, so that is the best bound. Yeah. And it works on samples, the most important part. And it's like linear, or n log n from binary search, and binary search is mostly fine in terms of constant. I'm gonna once again check the audio. Just checking obsessively now. I just want this to work. Okay. Test 22. Nice. Alright, that's another problem. Binary string partition. Let's call string t beautiful if either the number of occurrences of character 0 is not greater than k, or the number of occurrences of character 1 is not greater than k, or both. Minimum possible number of beautiful strings. For every k, find the minimum possible number of strings such that s can be divided into them. Time limit, 2 seconds. I mean, there's an n-log squared solution where we do binary search on the sums, but maybe that's not intended. Although I don't see why it wouldn't be. Remember there was some way to do I remember there was some way that I was able to do this and then log in before with some other problem. I don't exactly remember now. Oh, it's also either. It's greedy, right? Because if we move one from one position to the other, then it just makes it harder later. Like, we find the point where this breaks. The thing is, the sum of the answer is n log n because of harmonic series stuff. But how do we do it, not slowly? So, string s equals in dot inster int n equals in dot int. Is binary search fine? I mean, probably. But I don't know, it is Kotlin, after all. How did I do this before? I don't know. Did I do an n-log squared before? Maybe I did. But okay. Is there a faster way to do this? I'm supposed to start from the beginning. Let me get some partition like this. Now this will move over. How are other people doing? Is there a fast solution to this? Some 218 milliseconds. Okay. I'm trying to remember the name of that contest so I can find the problem. What was it? I know it was Rick and Morty. Let me see. I know it was Rick and Morty themed, so maybe I can find it from that. Yes, this. Perfect. No, I think this is just implementation. Never mind, it's still on login. Like, also, it shouldn't be that bad. I really don't know. I guess it can't hurt to try. Alright, so k equals 1, k is equal to n, k equals plus. We can build prefix sums. Plus r, p sum I plus 1 is equal to r. Doing one index thing because it's nicer. Now, int ants is equal to 0, l is equal to 0, while l is less than n, plus ants. Now we find the best r. LV equals 0, RV is equal to this should be int. Int MV equals LV plus. I don't trust the Java compiler. Maybe this is faster. Now, if psum int c1 is equal to psum rv minus psum l mv, int c0 is equal to the length of the string, which is mv minus l plus 1 minus c1. If c0 is greater than k or c1 is greater than k, then r is equal to m. Like, we have to go, this string is too long, so we have to go back. Otherwise, LV is equal to MV plus 1. And I think the answer, L equals LV. This should be fine. Let's see. Nope. Still no test cases. Okay. So out.println L plus. Where's it getting stuck? Is this the problem? Wait, is it because I'm doing that? Nope. Why is it getting stuck then? What exactly is the problem? Seriously, why are you getting stuck? Oh, that's why. Because this should just be s.length. Right, okay. Now we're gonna have some dumb bugs. Let's see if I can get rid of this and still have it work. No, okay. Awesome. So, and, right. If either one is over, that's fine. Cool. Yeah, okay. So the worst case is I'm gonna save this here. So if I mod 2 is equal to 1, so I'm basically putting the string of 0, 1, 0, 1, 0, 1. Then n equals 200,000. Right? Yeah. How slow is it? Let's see. I'll make it 20,000. I think 0, 1, 0, 1, 0, 1 is the worst case. If I make it 20,000 here on the running time, hoping it's a logic error and not the program being slow. What? Oh, wait. That's fine. What's going on? Why is this dying? I'm not reading in anything. What? What is happening? I'm just gonna stick this everywhere. Where are you dying? Are you running the right program? I don't understand. What is happening? Why do I need to read in a string? I commented this out. What is it compiling? What are you compiling? I'm gonna reset Sigma. Genuinely, what are you compiling? I'm so confused. Do you guys understand this? Am I reading in something? Like, I don't have test cases. I don't have anything. Where is it reading this in? Oh my god. Where is it reading this in? What could it be reading? What are you doing? It's doing some sort of... Genuinely have to comment out my entire program to make it not reading the string. Can someone who like understands Java tell me what is going on here? Is this like, am I gonna figure this out later and just like scream myself for being an idiot? I don't understand. What is it reading? What is it reading? Why is init.io forcing it to read something? This has never been an issue before. Literally never. It's never been an issue. Until now. I'm gonna manually delete the jar file. See if that does something. Just get rid of this. And get rid of that. I don't understand what it's reading. What are you reading? Does it work on Codeforces? Or is this just like the code itself that's causing some problems? Java, right? So I can just like do this. Is it because of the... Okay, whatever. Where are you stopped? Why are there so many issues with this? Now, this is also wrong, isn't it? Why is this not wrong? One more 2 is equal to 1. How is this not wrong? Where's 50,000 come from? It's 200,000. Oh, exceeding. Okay. Okay, fine. I'm just confused now. I'm just mad at whatever that was. I guess like to initialize itself, it just has to read in something. I really don't understand. Anyway, who needs speed? Just threw that out the window at this point. Okay. Biome map. Map is a matrix divided into cells of 1 by 1. Each cell of the map must contain one of the available biomes. Each biome is defined by 2 parameters. Wrong answer. Huh? How? Is greedy wrong or something? Find the number of possible beautiful strings. Is it a large test? It's not a large test. Should get rid of that. I don't know. Maybe it's some other stupid Java thing. S.char I is equal to 1, then plus plus r. So keep a prefix sum of the ones. Now, for each k, solve independently. Keep track of the answer. L equals 0. While L is less than n. Search for the next bound. So the string doesn't work, move the right bound over. Otherwise the string does work, so move the left bound over. So what's wrong here? Int n equals s dot length, and p sum equals new int of length n plus 1. So, oh, was that the input already? No. Okay, so it requires 3 here. 010, 101, 010. Wait, that's wrong. That is wrong. Okay. Good, that is something wrong. Right? It should be 4. Why does it get to 4 here? MV minus L plus 1. Oh, MV plus 1. Because this is how indexing works, right? Good, okay. Yes. Okay, good. Because I did one indexing and I'm not used to that, so I guess that's like, yeah. Probably note to self, don't like screw with your own conventions, because then you just like confuse yourself, exactly as what happened here. Now I was about to submit raw Java code, so let's not do that. Can't even count the number of times I've tried to do that in practice. And succeeded, for that matter. I guess it's fine, might still have TL issues, or time limit issues. I don't know. Biome map. Polycarp decided to generate a new biome map for his game. Map is a matrix divided into cells 1 by 1. Each cell must contain one of the available biomes. Okay, so I was concerned about time for nothing. Each biome is defined by 2 parameters, temperature and humidity. Wait, this was... I guess, yeah, it's similar time, even though it's n log squared, which I don't get. So either tests are weak, or... I mean, I don't think so, actually, because 010101 ran really quickly. Oh no, I guess the constant is light. Each biome is temperature and humidity. Each cell in the map belongs to exactly 1 biome. Each available biome has that. Okay. So somehow we just need to so first checkerboard. Yeah. Then with checkerboard, what? Temperature and humidity. Oh, it's all 100. Yeah, it's all 10. Interesting. Oh, we get a row and column for each different biome. Interesting. So the biomes will have to form a component. Like if you connect biomes based on the things that can be adjacent, then they have to form a component. Is there anything else about them? For instance, and that's why we get one for each row and column. That's a lot of test cases. Most of the identifiers are weird. Okay. So when is it not possible? Yeah, I guess the only time when it's not possible is when they have like a broken component. Now each cell can only be adjacent to a certain number of things. We just need some sort of construction. Suppose the cell is all the glory. also not necessarily like perfectly bipartite. Doesn't have to be. So if we had some like weird shape of biomes like this, like some weird shape like something like that, like you get the point. Then this is the hard case to deal with, I guess. Put this like somewhere. Like we start somewhere. Next biome has to be adjacent. Maybe like go back here or something. Can we somehow make it so like every biome sort of gets its own row? I don't know if that's possible. So like essentially we can create a, what did I just do? Okay, we can create a row and column. We can give each biome like its own row and column, for example. So like what if I made it so everything on this side is blue? And suppose this is cyan. Make it so everything here is cyan. Suppose this is green. So I make it so everything here is green. And suppose this is like gray. And I can't make it so everything here is gray, but I can do it for everything here. And this is like lime or something, and this can be like this. And then orange can be here. And I would handle like this shape. And then we just fill in the gaps. And we're doing some sort of like DFS on it. Right, so the gray is kind of the crucial part, that we switch the rows every time. So that now we can fill in the gaps like this. And then this can be like this. I missed one. And this can be like this. And then this can be any of these colors. So for example, that. And then this would be lime. So that way, every time we do something with the same parity, then it would be attached to like how would this work actually? Wait, this is sort of a simplified example. Would it extend more? Let's try like this. And then like this. Except we split it like this. So red, orange, green. Something weird like this. And then we split it arbitrarily here. Alright, so then what does this look like? I think this runs into problems. Yeah, somehow we have to make use of the fact that we have like 4 different directions to go. Because here we can maybe split this here, and then that works. But if we like come in from something like this, then we have to do 3 things at once, and it's not really possible. Can we do grid-like? Like for example, like this? I feel like we can't. Because then like sort of forcing ourselves to have... Will this work? This is kind of an interesting idea. That wouldn't work for like more than one split point. That forces our tree to be like a star, which is not always the case. Like in a shape like above, if we start from middle, like this is a hard shape to deal with. If we can make 2K, then we'll be good. Is the thing. Nope, I don't think that's happening. This feels similar to some other problem from Codeforces, I think. I didn't understand that one, so. I feel like it might be copyable, actually. Are there more solves on H? Where am I right now? Okay, not the worst. I guess we're fine. Would not hurt to have G, though. TLE. I remember there was some contests where, like, H is, like, a thing. Huh, did one. Oh, no, VK cup. Okay. Wait, so... It was... something I'd done. This one? Yeah, it's probably this one. What is this question? What is this problem ask? Right, so this is like strictly harder. So how does this problem work? They not have code. Are you serious? God, this contest sucks. To calculate inside J. So this is even easier. Let's see, I wonder if anyone wrote this in Java. I'm sure they did. This is just like work. We just like straight up copy this. I'm pretty sure this is the exact same problem. I might be wrong. Interesting. This is someone else who's doing this contest. This was not fast. Is Kotlin slower? None. How's C++? 1871. It's just not fast. But this is also half the runtime. So maybe it's just better. If I copied this, how would they feel about it? Please accept it. Maybe I'll try this later. It's like the only accepted submission in Java, and it's by someone who's doing this contest. I'll think about G more and then maybe copy paste it later. Yeah, this is like lower constraints, has K up to 5. Let's just see. Put in a credit comment. Which was written like 2 weeks before the contest, so it's fine. I pasted it in the wrong place. That's simple work. We don't need this, we just need so s dot char at x minus 1 minus a. This works for Java. This is fine, this is fine. There's so many vars. Oh my God. Okay, so this has N and M. Does it still work for this? Okay, this is for each column. This need to be long. I have to be. Oh wait, no, this is harder. Or maybe. Oh wait, never mind. Okay, good. It's not exactly the same, I guess. Alright, fine. Because that, I remember now. That asks for squares. This asks for matrix submatrices. Okay, so G is probably better. Let's just get rid of this for now. G is probably better. I don't get how to do G. Like, suppose we take the spanning tree and it's something like that. Taking a spanning tree is a strictly harder problem, so I guess it's fine if we do it. Can we solve it for a tree? What if we do some like weird square construction? Like, so for example, we pick a root like this. I remember this was a construction used to go before. We do like this, and then we do something like, now the remainder of this square is going to be given to this stuff. And so now we construct this to satisfy this subtree, and then we construct this to satisfy this subtree, for example. Right, so what does that give us? Does that help somehow? Well, as long as we can like merge the two. Somehow we need to fill in the gaps then. Can we fill in the gaps somehow? So we solve for that. How do we fill in the gaps? Well, maybe there isn't an intersection, which would be a problem. Yeah, it is kind of a problem. Okay, that wouldn't work either. Think about it like by particulars, maybe. Every vertex has degree at most 4. That's a thing. Like we could, in a certain amount of time, return to the root. Like we start from the root, we go down one of the subtrees, we end up back at the root. To do it in less than to time. Or just like somehow handle the intersection parts. Like, we just need to think about a way to handle like a cross, for example. How do we handle a cross? This is like the simplest case. Do something like this, and then like that. How do we handle this? Imagine if we just like embedded this shape. Would that work somehow? Is that what we're supposed to do? If we just like embedded this shape, then somehow filled in the gaps. The question is, how do we fill in the gaps? Okay, suppose we do embed this shape. Then like, probably doesn't work. Because sometimes we have like holes, and that is problems. Yeah, there would not be a way to embed this. Okay, never mind. So there goes another idea. What else can we do? We can somehow guarantee that we introduce a new thing in every time. Is that a possibility? What if we like start from here, DFS down here, the thing is we're just like slow. So suppose I put this down like this. This would be the way it works with this. Alright, then like this would be red. So that'd be blue. This would be something like that, and this would be something like that. Like this would work, but how do we continue this? Because it wouldn't work for like more complex shapes. Like if I stuck a gray on the end of this, there'd be no place to put the gray. Could we somehow like within here solve for the cyan tree? What if we did? What if we tried to do that? Like for example here. I'm running out of examples. So we use this again. Running out of space. Cool. Throw our pen across the room. So we put like the orange one like so that spans across here. And then we put whatever's on each of its sides on each of its sides. Now, no other vertex has to be 4, but that doesn't mean it's all settled. So this gets all of this. So suppose we have this color out of color. Use this. No, it's too similar. Use red. Right. So suppose we have like red down here, and we don't. Red is kind of annoying. I want to deal with this subtree. So first, this has to be orange, like by necessity. Maybe this is orange. Oh no. Yeah, this would have to be orange. We have to keep that there. Now somehow we introduce this in. So maybe we do it like this. And this side is already handled, so I don't need this anymore. Well, actually, this has to be here is the other constraint. And how do we do the rest of these? And we can make all these whatever we want. The problem is we still have to handle the subtrees. Alright, I'm gonna go to the bathroom and then come back and then maybe solve this or something. Just mute the mic like this, and then hope it doesn't break. Okay, pray this worked. Tap. Good. Okay. How does this timing work out? I guess that makes sense. Right, okay. So when is it? Yeah, if they're disconnected, it's definitely not possible. If they're connected, is it also possible? Is it also maybe the case that it's not possible? Seems like it wouldn't be. Like, how do they handle this? Oh, it's not that deep. So I can do something dumb like that. So we can use up to a 12 by 12 grid here, right? Can we somehow think better than 2D? So like, we can start with like this. Use a lot of different colors. Like this thing. You can tell the difference. I don't know. I use purple as well. And so like, suppose we just put this down. Okay, now we have this. And then maybe we like do all of these. Okay, so now we are forced to put oranges here. So now maybe on this side we can expand farther. So we can put these here and put this here. And we can put this here. Oh wait, I never thought about diagonally. Maybe that works out? Diagonal splitting. For example here, right? Now these once again have to be orange, these have to be orange, these have to be orange, these have to be orange. Problem is like with the complex trees, this doesn't work so well. Also, like, how many vertices are we using here? I don't know, maybe we can afford to do extra somehow. So we think diagonally. Now this has to be whatever's adjacent to yellow. In this case, it can be this. What if we have multiple things adjacent to yellow? Like in a spanning tree, for example. If we're gonna divide and conquer, then we have to handle all the things adjacent to yellow separately. It's basically like we could do it diagonally. Wait. Okay, wait. Consider the spanning tree. What if we did it just like this? So we do like this, and then like this, and then like this, and then like this. Then we return here. Then we do this again. Then we return here. And then we go like this. And so this would like fill up this diagonal. And so that way everything is adjacent. And we're essentially just doing DFS over the spanning tree, which is at most m-1. And we have exactly 2 m-1 diagonals. Oh my god, that works. Okay, cool. Okay, now screw up implementation. Wait, I'm pretty sure this works, right? Let's just think about it a bit more. So essentially, we're doing like, actually, how many things does it use? Let's make sure we're not off by 1 here. So for example, we can go down here. We don't need to come back until we do again, but we should always at least save 1 vertex, right? We go down here, we go back up. Every edge uses 2 layers. And the number of layers we have is, it's 2n minus 1. Okay, actually, this is totally fine. Alright. So basically we're doing like an Euler tour of the tree, and then we're putting that order in the, yeah, we're putting the Euler tour inside the matrix. That's cool. I like that. This is cool. The problems from Kotlin here have always been like standardy and stuff like that, but this is actually nice. I like this. This is a cool construction. Okay, and I'm gonna have to prove it works, and I have to figure out how to do DFS in Java. It's fine, right? I've done it before. Have I ever done a tree problem on Java? I don't know if I have. Okay, anyway. So int static int grid. Static int count. So static int nm. So n is equal to in.nint, m is equal to in.nint, g is equal to new int nm, for int I equals 0, I is less than n, I plus plus, for int j equals 0, j is less than m, j plus plus. Static dr4 dc. We can make this like 0, 0, negative 1, 1 in no particular order. Okay, now static the Euler tour actually perfect. This is actually perfect. This is exactly perfect. That's hilarious. Int. So array list integer tor. So tor. Does this work? Okay, I don't know why that's a problem, but let's leave the other compilers. Cool. DFS ij break. If count is not equal to 0, out.println -1, else. Cool. Out.println our count. Actually, I guess like the other tor is always a blank n, isn't it? Or 2n minus 1. So we visit this vertex. We visit the root first. Then for every vertex other than the root, we go down it, we visit, we go up, we visit the root again. So it's the sum of the degrees plus 1 because we start with the root. Like it should be that. Okay. Static void dfs int r int c. So tor.push add grc. And then this. Right. So for int d equals 0, d is less than 4, d plus plus. This rc int nr is equal to dr plus drd c plus dcd. Does this work or does Java have a problem? Okay, this rc equals true. If 0 is less than equal to nr, and nr is less than n, and 0 is less than equal to nc, and then nc is less than m. If g, nr, and c is not equal to 0, and this, not this, that cell, dfs nr and c, tor.add grc. Doubt it'll work, but yeah, okay. Wait, what? Oh, test cases. Good idea. Awesome. Okay. Right, I have to do minus count. Okay, count is -1 here. How does that work? What? So if that works, g, nr, and c is not equal to 0, and this has not been visited. dfs nr and c, tor, add it to the tor. Huh? Okay, so what's happening here? So count is 3, count is -1. Out dot println. Okay, DFS 0, 1, 1, 1. Why do we return? How can we return? DFS 0, 1. What? How are we revisiting vertices? If this RC return. Java bewilders me. What? How? Oh, wait, that's why. If count is less than our count, break. That's why. Okay, now we should be able to get rid of this. So count 3, count is 0. Yep. So 2, 1, 2, 5, 2. Good. So 3, 5, 1, 5, 6, 7, 6, 5, 3, 4, 9. Java assert. This works, right? Okay. Okay, now let's see how we do this. So 4 int goes 0 as an n I plus plus. 4 int j is equal to I, j is greater than 0. Or wait, k is equal to 0, k is less than equal to I, k plus plus. So grid I minus k, k is equal to tor.get I. 4 int j equals 1, j is than m, j plus plus. Int k is equal to 0, k is less than, should be r count. So if j is r count minus 1, that means, yeah, okay, r count minus j. If j is r count minus 2, that means we should go up by 2. J is r count minus 2, then we should go up to 2. R count minus j, k plus plus. Grid, so let's see. It should be r count minus 1 minus k, j plus k is equal to tor.get r count plus j. Is that the case? R count plus j minus 1. If we have R count, so we have 3. Just work their examples in my head. So let's say we have 3. So 0, 1, 2. So this should start at 3. So this should be minus 1. Yes. Out.print grid ij plus. Okay. Nope, this should be R count. This should be R count. That's weird. What is it doing? 10, 10. So it's just like not doing that. Or maybe it's staggered. Why does it stagger the inputs and the outputs? Okay. 1, paste. Okay. 2, 1, 2, 5, 2. Perfect. 1, paste. Back to 3. -1. Let's get rid of the debug prints. One. Good. Yeah, seems good. So n, m, reading the values, keep the count, keep the tor. We reset between test cases. We should actually check that we reset between test cases. I think it all looks good. Yeah, it's still intact. It just looks really weird because it's interleaved. So let's see, G is reset, this is reset, count is reset, N and M are readed in. These are global. Tor is good. Tor is reset. So Gij is new int. So we find any cell DFS from it. So I don't understand why we need this. Oh wait, yeah I do. Okay. So that's fine. It's actually okay to do this. Yeah. It's fine to have it just in case. So add it to the tor. Minus count. Yeah. So nr, nrn, nc, ncm, c, dc. Yep. So go up to that, and then have k go up to that, and then like leave them diagonally, and then have 1 to r count, and then yeah. I think it works. R count -1 minus k, j plus k. Cool. I just hope this compiles. It would be very cool if it did compile. Submit code. G. Does it compile? Compilation here. Why? Where? Are you serious? I hate Colin. God, what? If I make this abstract, will it work? You have to just like pass this in. That's fine. Fine. Int. Jeeves. I guess I can do that. I don't really want to deal with it otherwise, so I guess it's fine. Yeah, okay. Alright. That should not have taken so long. I think just because I didn't think about diagonals, which was like fun. Yeah, diagonals are important. They matter. Everything matters. Is there a compilation error here? Does this work? I hope you work. You better work. You're mad if you don't. I did what you wanted me to. Yeah, I don't think I have time for these two. Test 1. Don't get wrong answer. Test 13. Nice. Okay, that's good. So 26th. Interesting. Alright, so somehow salt I. Insights and Saratoga. Is this easier somehow? Calculate the number of submatrices that contain exactly k different letters. So 26 choose 5 is massive. You can't do that. I guess you can use the same idea. I don't know. I don't know the original idea, so I don't know how to do this, I'm pretty sure. Here, and bus routes to go along the bridges, and allow tourists to go from that. Okay. We have like not this long of a statement. Just first starts the excursion day at some site. And tour guides. Lead them to angles each site. Transfer angles. So it's a bipartite graph, I guess. Is it some flow problem? So how's this work? I'm asking for like 2 different matchings or something. constraints make it seem like flow. How do we propose it as flow? Oh, cool. Select flow. I don't know how to compose. Okay. So we need like all the stuff to go from one side to the other. And then like the cost is essentially it's the number of edges that we take twice. It's like we're going here and move down these roads. And from some things back. I don't have time. But I can still try. That looks fun. I don't want to do it. Yeah, maybe this feels like it's been existent before. Possible number of tourists. Yeah. Essentially, we're taking an edge twice. Or if we take an edge twice, then it hurts us. If we don't, then everything is fine. a unit flow there. Each thing is like, it has capacity too, but it also like doesn't. And then some has to go on here. Here, and then every torus side must be used once. Actually, if we reuse edges, it should be fine. Maybe I can do it in Java. Java min cost flow. Is this like a thing? I can try it. Why not? Turn total cost. Can I pull this off? I feel like it's like, it should be a thing. How do you use this? Yeah. Okay, let's see. So, so 2 cap xy is equal to, wait, that doesn't allow multiple edges. Okay. Cap xx plus xy is equal to 1. Cost xx plus xy is equal to a x. Flow dot get max flow cap cost. Wait, okay, right? So we need like plus 2. Cap xxx plus 1 is equal to n1 plus n2. Cap xx 1 I is equal to 2. Cap I plus n1 xx plus 2 is equal to, this can be infinite capacity, right? No, it has to be, in particular, it has to be 2 as well. No, it can be infinite, yeah. So capacity, cost, xxx plus 1, xxx plus 2. And 1. Test case. Okay, let's see why. Because I'm giving it too much freedom. So the total flow should be 4. 2, right? Alright, right. Cap x I xx plus I is equal to 100,000. $30. Okay. Yeah, this isn't gonna work. I think maybe with more time. I don't know. What could we have done? I think we probably could have gotten I. Not in the worst position. Anyway. Yeah, I don't know. I don't know if this is correct. I guess I can try and solve it. Plus n2 is 0 is an m plus x, y is equal to x. X is equal to 2 times n plus n2. These are weird names. So capacity of that is that. Wait, what is the sample? Why would it use that when it can do better? Oh, put down that into a flow. How is the flow 4? I didn't even give it that much. Oh wait, that's why. Is that the problem? Let's see if it works. I don't know. I feel like it's probably wrong, but it also might not be. There's this assumption I made that I haven't really I don't have any semblance of proof for, but it's worth a shot. Yes, this is fine. I hope it's not correct, because this was like minutes off. Compilation error. I hate Kotlin. Okay, well, I would not have been able to make that compile, so I guess that settles it. People AK'd this round. It's about a better time. And then it just went downhill from there. A lot of people with like one of these three. And then some people without one. Yeah, getting by with 6 is not something I could have done. Like 130. So I have 162, which would be around here, and that would not have done it. Cool. Was this TLE? I guess so. Alright, so I don't know how to do this. I kind of want to try and fix this. But like also like oh my god. Like, what? This is not allowed. What is this language? How are you not able to have declarations? I want declarations. That's what I searched. Okay, there we go. So that's what I have to do? Is there a way to get around this? Kotlin, not Kotlin. Late in it. That's a thing. Can I just like stick this in, it'll work? Yeah. Cool. Just put this everywhere. Okay. See if that works. Still think it'll be wrong. It's very possible that it will. Okay, good. Let's see. Is this some small test that I can't see it? Right. Alright, God, I just want to be done with this. So I'm just gonna go over A to G and then like be done with this contest. Yeah. H has so many solves too. Maybe, is it easier to do it with submatrices instead of squares? I mean, maybe, like suppose you're at some point. If you fix some pair of rows and columns. Then there's at most like one, if you fix a pair of rows and columns, then there's like, or if you fix like a pair of rows, for example. Like you can probably pre-compute that stuff, but that's in cube, so you have to do better. So maybe it's like, it's still like the histogram thing or something. I don't know. I don't want to think about it. There's a lot of diagrams. I'll just do the solutions I did think of, and then, yeah. Also, these statements are fairly simple, so I won't read them. Also, because I am lazy right now. So for problem A, essentially, you are here. You want to find the endpoint of the largest interval that contains your, you want to find the largest endpoint of all intervals that contain your point. So like to check if the interval contains your point, you have something like Li and then X and then Ri. So first Li has, like X has to be between Li and Ri. And if that's the case, then you can consider that point. And then the number of days that you can stay is the length of this interval essentially, which is Ri minus X plus 1. So essentially you can check if the interval contains it, and then if so, you can just take the maximum of the answer and like take the maximum of those. You can also it also works to check like only if li is less than or equal to x, and then you can like, instead of this, you use like the maximum of 0 in that, because maybe Ri is like on this side of x, in which case you'll end up staying for a negative amount of days. But it's actually fine to do that as long as you like don't print a negative answer. Instead, you just take 0. So like, you can sort of ignore the Ri condition, but it's like, it's pointless anyway. There's no reason to like do it, but it might save some time in coding, I guess. I don't know. Doesn't really matter that much. Okay, for this one, essentially the criterion is like, say you have 2 points that are equal distance to each other. Or no, that doesn't make any sense. Say you have 2 points. You want to put another point in that has like the same distance between 2 adjacent points. So like in sorted order, we're only considering the 2 adjacent points because there's no point otherwise. Like if we're considering these 2 points, and then we put some point, for example, between these, then the nearest point function will consider this. It'll consider whatever's on the other side. It'll consider this. So some other point will be blocking it, so there's no point to consider those points. So we only consider adjacent points, and we need to see if we can put some value in between that is exactly in between these. And so the way to do that is simply the midpoint of these is like, say this is a and this is b, then this is a plus b over 2. So if this is an integer, then this works, and if it's not an integer, because y has to be an integer, then that won't work. So a plus b over 2 is an integer only if a plus b is even. So yeah. And it's also the same parity as b minus a. So if they have like even distance from each other, that's also a sufficient condition to check. So essentially we go through adjacent pairs of points, and we check if points are adjacent to each other. No, we go through adjacent pairs of points. I don't know what I'm saying. And we check if any adjacent pair is like an even distance. And if so, then the midpoint between them will be an integer, and so we can do it. If not, then the answer is no. I'm also not going over code just because like, I don't know how Kotlin works, so I can't explain this that well. So I'm sorry. Yeah, this is one of the drawbacks of using Java, that I don't even understand the code I'm putting out. Which one was this? Where was the... Oh, that was the practice one. Right, okay. So this one's sort of implementation based. Essentially consider the string we have. I think the sample was 0, 0, 0, 1, 1, 1. Actually, I don't know how to prove the complexity of this. I guess it's like not that bad, right? I might have accidentally like implemented n squared log n. It just passed by mistake, or it's not by mistake. It's like fine. So basically, like what I just did was I just like did it like as naively as possible. You start here, make the jumps, and then you start here, then you cross out this cell, and you jump to the next cell. And if it's not crossed out, then you say like, we needed to jump k cells before, now we only need to jump k minus 1. So we jump here, now we need to jump k minus 2. So in this case, if k is 4, then we have 4 cells left to go. At here, now we have 3 cells left to go. At here, now we have 2 cells left to go. Here, now we have 1. Here, now we have 0. So now we've done the jumps, so now we cross out this one. Then we continue. So here we have, so now we have 4 cells, now we have 3 cells left to go. We go back here, This is still 3 because the cell is already crossed out. Now we have 2 cells left to go, 1 cell left to go, and 0. Then we continue on, we jump. So 3, 2, 1, 0. Wait. I don't know if that makes sense. Yeah, okay. Right, so yeah, essentially we're just going through, we look at each cell naively and we just like go through the array and figure out what happens. Another way to do it is you can remove the bad elements. So for example, after I do this, then I remove this element, so now I'm only working with this. And then when I cross out this one, then I remove it, so I'm only working with this, and then it's easier. Although even if you go through the crossed out cells, the complexity is like at worst n squared log n. Proof maybe, I don't know. The basic idea for it is like, essentially every time you go around, if you have x cells remaining, then you get at least x every time you go around. So in total, a single iteration is at most like n times n over x. N because you have to go around, and then n over x because that's the number of times you have to go around. Maybe like ceilinged, but it doesn't really matter. And so the total is like n times n over 1 plus n over 2 plus n over 3 plus dot 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 plus n over n. Or like k. I guess k, but it doesn't matter. It's like this can all be k. Sure. Doesn't really matter, right? So then, because like k is approximately n anyway, so it might as well be n squared. So this sum is actually k log k. I might link a proof to that in the description, but the basic idea is, so this in total is nk log k, or nk log n, or like something. Nk log something, right? And so, yeah, apparently it passes. I don't know. I expected it to be, I guess it's fine. I don't really know what to say about it. Like it just works because that's the complexity. So brute force what seems like n cubed but actually isn't. Or you can be smart and remove elements from the array so that every jump is worthwhile, and so it's strictly n squared. Every jump like gets you a step further. Okay, this one's just like a thing. Like you have this, you basically like you have this query string. Instead of thinking about adding one character to the original string, you can instead think about removing one character from the query string. For example, if we have A, B, C, D, we can say, for example, maybe we added A to one of the original strings. So maybe we had B, C, D before, and now we add A. So essentially, now we're looking for what string can we add A to get B, C, D. And that's the string you get when you remove A. This is the original string, and then you add A, then you get the query string. So you can consider removing A, and now you have a possibility of BCD. So every string that's initially BCD will match. You can also remove B. So now every initial string that's ACD will match. You can remove C, and you get ABD, and you get ABC. And now you just need to know the number of initial strings that match this. That like match any of these. And so basically you can just like store a map that maps string to counts, and then like you can count the number of BCDs with this map, and then it should be like log n or something. And so in total a query is m times the complexity of the map. So in total it's like n log n, or like n times map, to insert everything into the map initially, and then maybe like an extra m factor or something, plus like qm log n. Yeah, It also helps to like hash strings because 27 to the 10th is like not that big. It's like it fits within a 64-bit integer. Because like the bound for long is like 2 to 63 or something. So what that means is you can hash the string. So like you can map A to 1 and then B to 2 and then etc. and then Z to 26. And then you can like do like polynomial hash or any sort of hash, and then you can turn it into an integer, and then it gets rid of like an M factor sort of. It gets rid of like it makes the map factor a lot nicer. Or maybe you can use a hash map and it takes care of it for you. I don't really know. I think either way it's fine. Yeah, but I did hashing, and then that's just mapping instead of strings, that's just integers. Or long specifically. So it works. All right, for E, essentially what we want to do is we want the array to be sorted, or we want suppose like we know the skill value. The strategy we're going to take is we're going to sort both of the arrays and then match them like that. And the reason is just because we can, it's better if I face this down, because like we can, or I guess it's sort of like exchange argumentsy. Suppose B is sorted because like we can do that. We'll just like rearrange the elements so that B is sorted and then the elements of A correspond to it, because like it doesn't matter if we do that. And now we'll prove that we want to sort A too. So like essentially suppose we have like A1, A2. This is sort of how exchange arguments work. Although there are better resources than this video, I'm just showing how to apply it to this problem, I guess. Now, suppose we know B1 is less than or equal to B2 because it's sorted. Now, suppose A1 is greater than A2. So the cost we get is B2 minus A2 and B1 minus A1. Right, so of course, B2 is the larger one, A2 is the smaller one, so this cost is definitely larger. So we sort of ignore this. But now what if we swap the two? Then what we get is B2 minus A1 because these will match, and then B1 minus A2 because these will match. So now B2 minus A1 is smaller because A1 is larger, and therefore the amount subtracted from this is larger. So this is a better cost than this. And what about these? Well, we gave the larger element to this one now. So B1, now this cost is larger than this one, but like by how much is the question. And the basic idea is that like the change is A1 minus A2. And the idea is like this cost isn't going to be worse than this one somehow. Or rather, this cost will not be worse than this one. Alright, and the reason is clear because B1 is less than or equal to B2. So this cost, yeah, actually we don't need this. So this cost is not worse than this one. And this cost is definitely not worse than this one. So if we do it so that if A1 is greater than A2, we swap them and so that instead A1 is less than or equal to B2, then the cost we will have will either be not worse or better. Because this cost is not worse or better than the original worst cost we had, and so is this one. And this one was irrelevant because like this one was just clearly like dominating it. So that's the idea for exchange arguments. Basically, like, if you can swap two adjacent elements and it makes it better, then you can, and it does make it, it makes it not worse. So you can always, you can do it and it'll still work. So there is an optimal answer where the values of A are sorted, and therefore you can like solve it like that. There are some better tutorials on exchange arguments that can help, probably. So anyway, assuming A is sorted now, what's going to happen? So we have this array B. Now we're interested in, like, suppose the query is like this green element. All right, so this green element is going to be somewhere in the array A. And then we're going to have some of the array A to the left of it and some of them to the right of it. Now we essentially just need to compute the worst costs for each of these independently. Now this, suppose this has like X elements and this has like Y elements. So this is mapping. So this right here is mapping the first X elements of A to the first X elements of B. So 0, X minus 1 to B of 0, X minus 1. Right, but it's always a prefix. It's always the same values. Or it's always the same length. It's always some constant number of elements. And like it's like a one-to-one mapping. And so what that means is there aren't that many possibilities for like the types of questions that we can ask about the things that are before the query element. Like in particular, we can ask about, say, like X equals 1 maybe, or X equals 2. And all we need to know is n values of X. I don't know if this is saying anything, but basically we can just pre-compute the prefix like maximum costs for this. So in this case, it's like B0 minus A0. And this is the maximum of B1 minus A1, B0 minus A0. And then like X equals 3 is like the maximum of B2 minus A2, and then whatever X equals 2 is, etc. And so to find this out, we can pre-compute the prefix maximums. And so for this, we can do the same thing. We're asking about mapping the last Y elements of A to the last Y elements of B. So it's the same idea, except we do it on a suffix. And then the final part is this. And this is just like it's a single value, so we can just say like, this is like, so this is index k, and this is like bk minus x, and that's just the cost, and we can take that directly. So the answer is the maximum over the prefix, the suffix, and the direct cost. And to find the position, just binary search. It's like a lot of different implementation things at once. Yeah, but it works out fine. So yeah, I don't want to think about this anymore. I do like this though. I'm going to save this for later. Late init. For binary string partition, for f, we do something that looks like brute force. So for each k, actually first and foremost, the greedy is the optimal strategy. Because like, suppose like you do something worse than the greedy. So for example, like you have some element here that could be in here instead, but you don't. Then this differs from the greedy strategy. But then like, this is going to contribute a 0 to here, and so it's going to make this interval harder. So it's going to make it harder to extend this interval in the future. But if we move to here instead, then this interval will be easier, and it would be of no cost to us, since we already determined that we can legally have this here. Like basically, like if you have anything that's not the greedy, you can like change it to the greedy and make the answer not worse. So greedy is optimal here. Right, so for this problem now, we just need to simulate the greedy algorithm, and we can actually just do that. Kind of. like for each k independently, for example, say we have 0, 0, I'm gonna use the bigger one, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0. I wrote that wrong here. All right. So essentially we're starting here. I'm not gonna use a 0. So we ask, from this position, how far can we go? And because we have a condition that just depends on the number of 1s and 0s, we can do binary search, because as we sweep right, the number of 1s and 0s will increase, or will not decrease, and therefore it's like monotonic and whatever. So we can binary search on the, if this is the left endpoint of the current like beautiful partition thing we have, then we're binary searching on the right endpoint. And yeah, so that works this way. Then once we binary search on this, now we have this, now we count this as part of the partition, now we have this new thing, then we do the same thing. We binary search once again, and then we just keep doing that. So suppose we have k equals 1, for example, then we would binary search, we would find that this is the longest we can do, then we would binary search again, we would find that this is the best we can do. Wait. Right? Wait. 1, 1. All right, and then this is the best we can do. So it gives us 3. Then for k equals 2, we do the same thing. We just like, for k equals 2, the best we can do is this, and then this, and then etc. It goes on. Right? So now the question is, why does this work? Wait, now I'm confused again. Why does it? No, I'm not confused about this. I'm confused about something else. Like when I had 0, 1, 0, 1, why is the answer that? K equals 1, and you have like 0, 1, 0, and you have 1, 0, 1. I don't think I understand. Whatever. So, yeah, sorry. So the question is, why does this pass? Why is it not n squared? Because like maybe the answer is n squared, right? Well, no, because the interval we take for some k is always at least of length 2k minus 1. Because for an interval to be invalid, we have to have, or actually 2k plus 1. For an interval to be invalid, we have to have greater than k zeros and greater than k ones, which would be of length 2k plus 2. So if we remove one of these conditions, for example, say we have less than or equal to k zeros or less than or equal to k ones, then it's 1 less than this, so we get 2k plus 1. So the sum of the answers for each string is at most the sum from I equals 1 to n of n over 2I plus 1. In particular, we can just ignore the plus 1 because it doesn't really matter, because we're thinking about asymptotics here. And it's like 1/2 the sum from I equals 1 to n of n over I. This is also a constant factor, so we can get rid of it. And as it turns out, as I said before in one of the other problems, I think it was C, this is O of n log n. Reason, again, I will put it in the description. I've proven this a lot before. It's basically just like, it's some cool trick with like fractions, basically. I think it'll make sense. I'll just show you the blog since I'm not in any way, any shape to explain it right now. So yeah, sorry. Today's just like a day. It's just like, it just is a day. I don't know what else to say about it. Today is just like, it's just a day, man. Last problem, then we can go. Yeah. So, first, for this problem G, it's okay to consider a spanning tree, because say we like have this graph here, it's like this. If we consider only the spanning tree, so for example, we assume that these are not adjacent and therefore we cannot have these next to each other, then it just makes the construction harder, or it makes it like not easier, because it only gets rid of things that can be adjacent. So if we can find an answer for the spanning tree, then it will work for the original one, because the spanning tree is a strictly harder problem. So, or like specifically not easier in any way, or a not easier problem in any way. So now we're working with the spanning tree. So essentially, consider the matrix that we have. It's not a square. What we can do is say like the problem says, like k is the number of total biomes we have. So then what that means is, what about the diagonals? Because if we have diagonals, then like everything in this diagonal is adjacent to this diagonal and this diagonal and this diagonal, and like nothing else. So like every diagonal is only adjacent to the two diagonals that are next to it, which means like we can sort of use the diagonals like an array essentially. And how many diagonals do we have? Well, it turns out to be 2k minus 1, because we have k diagonals on this side and k diagonals on this side, except this one overlaps, so we subtract 1. So now instead of like a matrix, now we're just working with an array of length 2k minus 1. And somehow we want to make it so on this array we can go through the biomes and like do some stuff with them. We can go through the biomes and have it so they're all adjacent. And so remember what I said about spanning trees. Essentially, like, consider a DFS traversal of some tree. I'll move past the matrix. Consider a DFS traversal of some tree. We want to traverse this tree so that we want to traverse this tree and write down like the numbers of the vertices in such a way that we always write down adjacent numbers. So you may be familiar with this by now. This is called an Euler-Tor. And the way it works is essentially we start by writing down the root. Then we move down to the next, we move down to some node, we write down that node. We move down to some node, we write down that node. When we have no children, we go back up and we write this down again. So that now 3 is adjacent to 2, so now we're back at 2, so now we can go down and continue going down to the children of 2. So now we can go to 4. Now we can go to 5. Now we can go to 4. Now we can go to 2. Now we go back to 1. Now continuing on, we do 6, we do 7, we do 8, we do 9, 7, we do 6, we do 9, we go back to 6, and then finally back to 1. If you were counting, this length is exactly 17, I'm pretty sure. Yeah. Which is exactly equal to 2n minus 1. Which is convenient, right? Because that's the exact amount of space we have on this matrix. That's the exact amount of diagonals we have. And it also has the property that every two numbers are adjacent in the tree. They're connected by an edge. And the reason it's 2n minus 1 is like, first we write down the root, then for each edge, we go down to the bottom node, write it down, and then go back up and write it down again. And like, look at each edge. Each edge has 2 arrows associated with it. So each edge will contribute exactly 2 numbers to the Tor, and the root is 1 more. So really we have, because the tree has n-1 edges, we have 2 times n-1 plus 1, which is equal to that, if you expand it out. So we take this Euler Tor, then we just like write it on the diagonals. That's it. So for example, let's take a simpler tree, like the one from the sample, 215. It also doesn't matter where you root it. Like you can just do it anywhere because the Euler Tor will always be this. It won't be the same, but it'll like always still work. So in this case, the Tor would be 2, go down to 1, go back up to 2, go down to 5, go back up to 2. So on the diagonals, on the first diagonal we write the 2, on the second we write the 1s, on the third we write the 5s, on the fourth we write, no, on the third we write the 2s, then we write the 5s, then we write a 2 again. Yeah. And so there's some like indexing stuff that you can do to write on the diagonals properly, but like it ends up working out, I think, probably. Yeah, I mean, I gotta accept it, so, you know, it's probably correct. Yeah, and, so we write it on the matrix, and then that's just the answer. And it, like, you can show that it satisfies the properties, and is exactly like 2k minus 1, and everything is perfect. So in one sentence, we take the Euler Tor, we write it on the diagonals. That's it. Or we take the Euler Tor of a spanning tree, and we write that on the diagonals. Let's see, you can see like on the sample I'm generating stuff like this, which sort of looks like diagonal stuff, and then here too, and etc. Yeah. Let me see if I can find out what's wrong with my eye. Or it's probably just like straight up wrong, but who knows. Yeah, it's a worse answer. Wait, it's a worse answer? That's not expected. But I made the graph more lenient. Anyway, my solution to I is some sort of like min-cost flow that I'm like, I don't understand. I don't have any sort of proof for why it's correct. I think there are some assumptions that are sort of like not easy to prove or something. So I'm not gonna try to explain it. And if I fix it, you can just like look at the network and I guess see how it works. I don't really know. There's some stuff going on. I don't know why the answer is worse. That's not expected. I expected it to be better, but whatever. Yeah, that was A to G. I guess I'm done. Hope you had more fun than I did. I don't know. I like G, I guess. That was fine. Yeah, okay. That's all I have. That's all I want to say. So, goodbye.